Hello, today it's my pleasure to talk about what I call the root of the challenge. So we're going to consider finding a root of a given function. What does that mean? And what does it mean to iterate? And we're going to look at 4 different iteration schemes. There's a Newton Raphson, there's a bisection, there's secant, and then there's false position. Let's start with a basic real analytic function, which is a polynomial in this case. And we're going to talk about the roots of this polynomial. So the polynomial is a quintic polynomial. That means it's 5th degree. And that means that I've got some coefficients that are starting and that are presented in ascending order. My terms are presented in ascending order. And the way I calculate it is I use the Horner technique, which starts with the highest order coefficient times x and adds the next coefficient before multiplying by x again, and then repeating until at the very end you add in the constant coefficient. So whenever we find some x values that make this f of x 0, that's a root. And since it's a quintic, we know that there are 5 roots. And if we go and calculate them, when we actually do the floating point calculations, we may not see those as being exact zeros. But in theory, there would be 5 roots that would make this polynomial vanish. In other words, equal 0. So I'm going to plot it first of all, and here's my code for plotting it. I've got my coefficients in the ascending order, and I'm going to plot with x starting at -1 and going all the way to 5 in 0.01 increments. And I'm going to call my Horner function, and I'm going to give the Horner function my ascending coefficients, and I'm going to give it the current x, and it's going to grab the y, and then it's going to plot it. So the Horner function, I'm going to let you kind of avail yourselves of this, and this is in my day 7 folder. But what happens is you send in the coefficients in ascending order for a, and then you give it the particular x that you want to evaluate the polynomial to, and it'll return the y value. So what happens is my y function, or my y value, starts out as the highest coefficient. Notice that that in MATLAB, of course, the indices start at 1, but I actually do the coefficients starting from 0 on the polynomial, and I take it up to the degree of the polynomial, 5 in this case. So they're off by 1. That's a little bit of a pain in the butt, but the way I handle it is I just do a +1 on my a, so that's how I handle it, and then the values that I'm indexing would be corresponding to the various powers. So notice that my for loop descends. It starts at n-1, n being would be the degree of the polynomial, because your coefficient array is going to have 1 more than the degree of the polynomial would have. So I'm going to let you thoroughly go through this and understand it. So I used the Horner to generate the values of the polynomial for the given x's that I had set up for the particular quintic. And then given all of the x's and all the y's, I plotted it. And let's see what that looked like. Here's what it looked like, and you can see that there's one of the roots you can see very nicely is 4, and then the other ones are kind of difficult because it's so flat over here and not a lot of variation, but we get that 4 very nicely. Now this is a little bit of a cheat, so you can use the MATLAB roots function, and if you give it the coefficients in descending order, so I have to flip mine in order to get the roots. So if you give the roots the coefficients in descending order, that's what roots is looking for. It's MATLAB function roots, MATLAB function flip, but that's what it does, and it gives you the the x value, the roots in descending order themselves. So there's the a, or the coefficients that we have for our quintic, and I just flipped them around. So this is a little bit of cheating here, but we're going to go in and find out what they really are. So I zoomed in on my graph. In that flat area, the first flat area, 3/8, I see that, right? Because I've got 3/8, I got 3/4, 1.5, and 2.5 reported by MATLAB. So there's the 3/8, there's 1.5, there's 2.5, and then there's the 3/4. So those are the roots in that little flat area. So with the polynomial, there is a little bit of a silver lining because of the fundamental theorem of algebra, and that a quintic, for example, is going to have up to 5 roots, 5 real roots, and if we were to think about them as complex, it would definitely have 5 roots always. So when we're rooting an analytic function, the objective is to start with some x value, see if by chance it's a root. Most likely it's not. And then we have to tweak that current x to a new x. And then we see if that new x is a root. So it's an iterative process where you guess an x, you see what you got, and then you make a new guess of an x and see what you got. So iterate. All right, so what we do is we're gonna take our quintic polynomial, and we're gonna think about this polynomial and look at it, the absolute value of our floating point calculation, and we're gonna see if it's less than some error. So getting this error is a big deal. So we want to make sure that that whatever x we have in the calculation of the polynomial here, that is a very small number. Take the absolute value of it, and we want to check it relative to this error. And if it's true, then that means that x to within floating point round off could be a root. Okay, so remember we did this for the quadratic, and we had this, what's really kind of a polynomial in itself. It's just that all the coefficients have been absoluted, coupled with the x's, and then there's some scalars that are multiplying the various coefficients, and then there's a machine epsilon that kind of multiplies all of it. So that was the error for the quadratic. Now the quintic is going to be obviously different, and that was actually a homework 2 problem, the figuring out what the quintic error is. So that's what we're going to do. So if we're searching for a root, okay, so we start off at the first iteration. So this marks your iterations, how many iterations you're going to have, right? So the first iteration, you're going to have a particular x, and then your polynomial value is going to be really, really high, way above error, and then you're going to try to make a new guess of an x, and you're hopefully that new value of x that you guess is going to lower that polynomial value. So ideally the polynomial value will diminish until you get below the error. Okay, you get below the error, and then you keep going. If you're going well, you just keep going until things start to kind of peter out, if you will. So this is iteration. So this would be starting at the beginning of the search, and this would be could be 10, could be 100 steps. I don't know, however many it is, and that's when you stop. So you want to make sure that you are below the error. The polynomial value is below the error. So that's, over here we're going to stop, and I'm going to tell you how to do that. So you want to make sure that your polynomial value, absolute, is less than error. And you also want to make sure, well, hell, if it starts to increase again, then, you stop then, obviously. But typically what I'll do is I'll check this tolerance here. And what this says is that the x that your x values aren't really changing. So there's no sense in continuing to iterate if your x just never moves, right? So that is that's what this is saying, that the x of the current one subtracted from the next x, absolute value of that, divided by the current x. If that's going to be less than some tolerance, then your x's aren't changing, and you're below so you might as well stop. So there's for the stopping criteria, there's at least 2 criteria that you have to satisfy before you stop your search. Okay, so the nature of the function that we're rooting in our case is a polynomial. So it's pretty straightforward, and I can go ahead and define the derivative of the polynomial very, very easily. The quintic is going to have this kind of derivative, which itself is a polynomial, actually. And then the bound. So here's the from the homework to solution. There's my for the quintic. And, it's got all of the coefficients absoluted, the x's absoluted, and then the x's to the various powers all the way up to 5. And then you can kind of go through the homework solution to see why there's a 10 that's scaling the A5 term. For the quintic, doing the Horner's method, there are 5 multiply and 5 additions. So 10 total operations. And that A5 sees all 10 operations. So that's why that's a 10. And this is a 9 because the only thing that A4 doesn't see is that very first A5 times x. And all of this gets multiplied by machine epsilon. So that's my and that's what I'm going to check it relative to. So what I also wanted to tell you is I've got this get coefficients, and it basically it does this for me. So it doesn't put the epsilon in there, but it gives me the coefficients of the polynomial decorated with the 3, 5, 7, 9, 3, 5, 7, 9, and 10, and all of the a's are absoluted. So that takes care of that too. I've got it kind of hard-coded for a quintic because the length is wanting to be 6. But that's there in my day 7 code. Okay, so let's talk about Newton Raphson. Okay, so Newton Raphson, you can think about the Taylor series and think about the next polynomial value for the next x that you're going to have would be equal to the current, the polynomial evaluated at the current x plus the derivative evaluated at the current x times the next x minus the current x. So that would be your h. So that's just a Taylor series first order step. Now, if we say we want to kind of hope that next polynomial value is going to be 0, so let's put in a 0 like that, and then let's solve for what that next x might be. So I take this equation and solve for this x k plus 1. So that's going to be my next guess. And that next guess is equal to the current guess minus the value of the polynomial divided by the value of the derivative of the polynomial, each evaluated at the current position. Okay, so if you look at over here in the image from the book, so I'd be starting here, my current xi, and which has an f of xi, so that's my current polynomial value, and I'm going to subtract off something along the slope to get me back over to here. So that's going to be my next point that I'm going to be looking for. Okay, so this is equation 6.6 of the book. This is Newton Raphson in all its glory. Very easy to implement. And here's how I implement it. So here's my code that I'm going to show you to run for Newton Raphson. And at the beginning, I get my polynomial coefficients in ascending order. That's my A. Here's the coefficients for my derivative, right? Because it's going to have 1, 2, 3, 4, 5. So we only have 5 because it's a quartic, right? So it's going to have the 5 because of the 128 of the x to the 5 x to the 5 term is going to bring that 5 down to multiply that. And then the x to the 4 term is going to bring that 4 down to multiply that, and then so on. And then I lose the constant term. So those are the coefficients for my derivative. And then as I said, I get my coefficients. I showed you that just a moment ago. So I get my polynomial coefficients squared away, one for the actual polynomial, one for the derivative, and then one for the Okay, and then the next thing is I initialize my first root. So I'm going to start, I know 4 is an answer. I'm going to start at 4.5, and I'm going to say that my iteration is 1. So I'm going to initialize my array of x's at 4.5 being the very first one. And then I'm going to let I'm going to create a for loop here. And I'm going to, at the top of them, I'm going to let that for loop go between 1 and 100. But you'll see in a moment that I figure out how to bust out of this when I'm happy, when I'm happy with everything. So right at the top, I'm going to calculate the value of the polynomial using my Horner function. I'm going to calculate the value of the derivative using my Horner function and the derivative coefficients. And then I'm going to calculate my My is going to be, it's going to come from the Horner of the error coefficients with the absolute value of my current x. And I'm going to multiply that by eps at the end. All right, so that's what I do. Then I do some debugging. I print out the current k, how many iterations. I print out my current x. I print out my current polynomial value, and I print out my current All right, and then here, so that's my debug. The next section here, this is where I decide if I'm good and I can bust out. So there's a break in here. There's a break, and what that break means is it's going to break out of this for loop, and it's going to end the program, and then the last printed thing is going to be what the answer is. Okay, so let's see if we can navigate how these two nested if statements work and why they are putting together two basic criteria here. All right, so the first thing is we're going to make sure that our polynomial, absolute of the polynomial, is less than the It's less than right? So I want that. Okay? So that's the first thing. And if that's true, then I want to go and make sure, I want to check to see if the x's are changing. If the x's are still changing, I'm going to keep going. If my polynomial is diminishing, and I'm making more progress, I'm going to keep going. So once the x stops changing, though, and that's what this is capturing, if this relative difference between the current x and the previous x, if that is not changing, if it's less than 2 eps, which is very minute, if that's true, I'm going to break. Before I get to that, though, I want to make sure that I have a k. I want to make sure that I'm not dividing by 0. Like pulling up a k that doesn't exist. Like on the first iteration, I want to make sure I'm not doing this test on the first iteration. So the first iteration, I won't do this and I won't do that. Right? And these double ampersands protect me. So that's called a short circuit and. So if this is false, it doesn't even calculate anything over here. All right, so let's say we're on a subsequent pass, and k is actually more than 1, so we make it past that. And I want to make sure that my x is not a perfect 0, because I'll be dividing by 0. I don't want to do that. So I make sure that I have an x, and then I go ahead and calculate this, and if it's less than 2x, and obviously, my polynomial is less than then I'm going to bust out, and I'm done. So that's the sort of the multiple criteria here is that that the x is a root to within floating point round off, and also that as we're searching, the x's that we're looking at aren't the x isn't changing. Okay, so that those are the two criteria. All right, so let's say that we're still going. So what we're going to do is we're going to use right here. So this is Newton Raphson. That is Newton Raphson. It's very straightforward. I take the current x value, I subtract off the current polynomial value divided by the current derivative, polynomial derivative. And that's going to give me my next x value. And then once I get back to the top, the k is going to increment. And now what was k plus 1 at the end of the previous loop is now going to be k. And then I just continue. All right. So that's a guess or a proposed next potential root. Okay, so here's my running of that script to NR, Newton Raphson. And you could see I started at 4.5, huge polynomial value. I didn't get these things to kind of line up because that was so big. My error is very, very small. And then you see that I'm kind of stepping in a good way because my polynomial value, it is diminishing. It is diminishing quite rapidly. And how many did I print here? My f value, I'm printing 16. Yeah, so I'm printing 16 and my getting some stuff out here on the back end. So one thing to note here is that the 9th iteration really had it, right? But if you compare the 9th iteration of x with the 8th iteration of x, there's a difference of 36 out here in the 15/16 place. So it's not going to satisfy. It's not going to satisfy that. It's not until the very last, that 10th iteration, where, yeah, there's no change in x, and there's also no change in f. F is 0 anyway. So that's why it ran an extra iteration there, was to satisfy this part here. Okay. And that's the point that we're looking at. There's our Newton Raphson, the first time through from 4.5. Then we jumped up 4.2, I guess. I beg your pardon. This was 4.2. This is 4.04. So the Newton Raphson took 10 iterations. Starting at 4.5, it took 10 iterations to find that x equal 4 root. So that's very instructive. So this is the basic rooting sort of technique, is where you have some initialization steps up here. You have a for loop. Then at the top of the for loop, you do your function evaluation, everything you need. Then you log it. Then you check your stop criteria to see if you're good. If you are good, then you break out of the for loop. And if you're not good, you want to keep going, then you do your rooting strategy. In this case was Newton Raphson. So we'll just use this over and over. We'll just make some minor tweaks to it. So that's Newton Raphson, and it's not a panacea, it turns out, because depending on what the curves might look like at a given point, it could shoot off. Like if we're at this point, it's going to shoot off that way. If we're at this point, it's going to shoot off here, which would drop us here, and that could put us in some infinite loop to where we're just kind of going back and forth. And then if we're above, if there's no sort of place where the curve actually crosses the x-axis, we may not actually find a root right there. So there's some issues here. So it's definitely not a panacea. Doesn't always work. There's some other methods I'm going to look at now with you. Bisection is going to be a bracketing method we're going to take a look at. So for bisection, what we're going to do is we're going to start with a lower and an upper x value that's bracketing the particular root that we're looking for. Like for example here, there's an XL and an XU. So low and high, and we're going to start in the middle. What you do is once you have a low and a high, or a lower and an upper, you take the average of those, and that's going to be your current location. And let's see if we can figure this out. If the polynomial, or the f at the lower and the f at the x, have the same SIGN, both negative, like in the first iteration over here, let's check this out. So I've got my x of k, which is going to be right in the middle. That's going to be the average of the XL and XU, so it's right in the middle. Now that function is going to be negative, just like the low is negative. So they're going to have the same SIGN. So what you're going to do is you're going to replace XL with XK. So XL is now going to be what was our XK, and then we're going to go do another iteration. So for this iteration, if you look at it, the average, which would be the XL plus XU in the middle, that's going to be above. So we're going to replace XU with the current XK, and then we're going to do the same thing again. So every iteration, you're dividing the previous segment by 2. The interval is divided by half every time. Okay, so let's see if we can figure out how to code that. So here's my script 2 BS. It's in my day 7 folder. So this is kind of the same, except for I'm going to bracket that the root of 4 that I know about. I'm going to bracket it between 3.75 and 4.5, and that's going to give me my first point as being the average of those two. And then I'm going to, I don't do the derivative here. I just evaluate the polynomial, and I evaluate the just like I did before. I print out my stuff like I did before, and then I do my test like I did before, my stop criteria. Sort of the new thing here is down at the bottom, where you see that I'm taking the new x left and x right and averaging them to give me my next xk plus 1. All right, so how do I do this? So how do I do this? Well, I've got my polynomial evaluated at the current x. I've got that f of k, and what I want to do is I want to go ahead and evaluate the polynomial at my x left or x lower, and see what its value is. And if its value times the current polynomial value, if that is greater than 0, that means that the left and the xk have the same sign, the function value, the polynomial values will have the same sign. And in that case, I'm going to replace the left with the x of k. Otherwise, I'm going to replace the right with the x of k. And that's all it is in the bisection. That's what we went through with this, stepping through the little example there. So how does this run? Well, actually, this script BS, when I ran it, it took 49 iterations, and then it finally gave up. So it gave up. I've got my polynomial value. Yes, it is less than the no problem. It is less than okay. And then if you look, it looks like my x's finally, my x started at 4 1/8, and then it sort of fluctuated around 4, and then it got down into this area. So it's going to be 18 in the 15/16 place above 4, and it was 36 below 4 in the 15/16 place, and then here it went above 44 in the 15/16 place, and then it's 36 in the 15/16 place. So in the 16th place, it's only off 8, so that's going to be less than this right here once I divide by 4. So that's what kicked me out, was the polynomial value. Yea, verily was less than as you can see, it had been for a while, and then finally the x stopped changing. So the value you're going to represent or declare is this 4 with some little fuzz here at the end. Now you might look at the left and right and say, well, what the heck's going on here? But I only printed 10. On my XL and XR, or X left, X right, X lower, X upper, however you want to look at it. I only printed 10 zeros, but I'm sure there's some fuzz that's kind of matriculating there. But bottom line, 49 iterations, and I got something that wasn't quite as good as the Newton Raphson, but it's pretty close. So that's the bisection method that I've just showed you there. It's a bracketing method. Next is the secant method. So the secant method is like Newton Raphson, but you actually use a finite difference in order to get the derivative, and that's that makes it a little bit easier. You won't have to calculate the derivative. You're just going to divide through, like on an ordinary pass. You're going to get that current derivative value as being the current polynomial value minus the previous one, divided by the difference in the respective x's, the current x minus the previous x. So you can do this as long as k is greater than 1. So when k is equal to 1, I've got to do a little fudge here. I've got to do a little manipulation in order to figure out what my derivative is going to be. So I do what I call a little perturbation. So I take a little minor step and figure out what the Horner value is, and subtract the current value and divide by that little mod secant step there. The 0.02 is what I've got it configured as. Okay, and then at that point, it looks a lot like Newton Raphson. So let's see how it performs. So interestingly, it's very close to what we found with Newton Raphson. 10 iterations, so no problem. Okay, the last type of iteration technique is called false position, and it's a bracketing technique, not that much different than the bisection technique. And I'm going to let you kind of work on this with in your homework. But what it has to do is it uses, instead of looking at left and right, it looks at the value of your current polynomial of your root, and kind of compares that with what you have on the lower, upper, left, and right. So I'm going to let you work on that with the homework. So we've today we started rooting around. We figured out what a root is. That's an x that makes our objective function or our analytical function vanish or equal to 0. We talked about 4 different iteration techniques, and we learned what iteration meant. We looked at the 4 techniques of Newton Raphson, bisection, secant, and we talked about false position. So hopefully you enjoyed it.